let's take a look at how robots powered by AI can help fuel innovation in industries. Here to help us understand this question is from Vicarious, Dilip George. Take it away.
Hello, everyone. So it's 2019, and we have cheap sensors, good plastic, cheap motors, and we also have social robots. But where is Rosie the robot? For those who don't know, this is Rosie the robot. This is from the Jetsons series. It's a very famous series. And this is a robot, household robot, that can do all kinds of things. It can entertain kids. It can give you a back rub. It can beat a rug. All these things. And this is fictional. It is not there. Why is that? The reason is that the AI that we have today is still very, very, very primitive. If you look at the history of evolution, starting around 600 million years ago, evolution created lots of creatures. And each of them had very sophisticated behaviors that let them thrive in their own niche. Although each of these behaviors were very sophisticated, they were still brittle. And AI today is still like that. Let me show you an example. So here is a creature, which is an old brain creature. It's a frog. It has a fly detector right on its retina. And its evolution created that, and it will go very effectively snapping at insects on an iPhone, even though it's not getting any nutrition. It has no, it has no way of changing its behavior, even though it is not getting its nutrition. And here is another example of a Roomba getting stuck in the corner and just cleaning the same corner again and again. And even the celebrated successes that we hear of AI from recent days are like this. This is reinforcement learning agents playing the game Atari, and here it is playing well. And on this slide, the same agent is struggling. What did I change from one setting to the other? I changed the brightness of the screen like 20%. So the agent that was playing well in the previous game stopped playing well at all. And here are examples of deep neural networks, which are the state of the art in AI, getting fooled by patterns that are artificially created. So for example, it will classify that wavy pattern as starfish, or that black and white pattern as penguin, with very high certainty. So many of you are worried about robots taking over the world and robot apocalypse, etc. So here is something for you to avoid the robot apocalypse. If you're worried about it, instead of wearing this T-shirt, you can wear this T-shirt, and the robot will think that you are a starfish, and you can escape all the apocalypse. So this is not surprising. If you think about how AI today is trained, you have a black box with adaptable parameters, and you gather a lot of training data. You call it the stimulus. You gather a bunch of labels, which is the response that you want for each stimulus, and you train this black box using an algorithm called gradient descent, or reinforcement learning, or evolutionary search. But what you get after you train is like a creature which has a stimulus to response mapping. When a stimulus comes in, it will give a response, but it has very limited capabilities for thinking, imagining, planning ahead, reasoning, all those things. So today's AI is like the old brain, and all the successes that we see, sophisticated as they are still like the old brain, like the frog. So how do we go how do we get to Rosie? So to do that, you need to do three things. One is learn insights from the neocortex, that's the new brain. The second is focus on data efficiency and task generality. I'll explain this. And third is build systems that can understand concepts like humans. So let me go through this. Evolution, later in the evolutionary cycle, came up with a new architecture. This is called the new brain. We all have it. This is what makes us intelligent. This is what makes us different from other creatures. And mammals have it. And of course, we have this brain and use it occasionally. And this is a picture of the neocortex. This is the structure that is put inside your skull. It's almost like a dinner napkin, which is crumpled and put into your skull. It sits on top of the old brain. The old brain is still there. And that is what is handling most of your primitive behaviors. But anything that you call intelligence, adaptive behavior, rational thinking, all those are controlled by this new structure, which is fundamentally different from how evolution created the old brain creatures. Rather than hacking each behavior, evolution created a new structure, which is the neocortex, and it is very regular and very prototypical everywhere. The piece that does vision is very similar to the piece that does language and audition, etc. So we need to understand the principles of that. We have lots of data about the neocortex. For example, these are examples of how the circuits in the neocortex are organized. They're organized in 6 layers, et cetera, et cetera. We have lots of data about it, but we need to understand the computational principles behind those organization. Not simulate it, not simulate the details of it. We need to understand the computational principles behind it and put that into our AI software. That's one. The second one is focus on data efficiency and task generality. Currently, AI systems are trained like this. We have virtually unlimited training data, and we train them to do a particular task, classify this set of images, and we test on a small set of test data. We want to flip that. If you want to build general AI, get to Rosie the robot, we have to flip this and say we have to train on very little data and test on unlimited data sets for robustness. And let me give you some work that we did as an example of the first 2 principles. This is the work that we published in Science. It was about breaking CAPTCHAs. We fundamentally broke text-based CAPTCHAs, and we got a lot of attention for this, but that's not the reason why we picked this problem to solve. CAPTCHAs are examples of data efficiency. I can show you all these text-based CAPTCHAs. You did not get any training example from any of them. I can show it to a 5-year-old child. A 5-year-old child will be able to solve most of these CAPTCHAs without getting training examples from them. And that's the way we approach the problem, too. And in fact, you don't even need to see all of them. Think of a single letter A, which can be rendered in so many different variations, and you can say that they're all A. And this is why this is really surprising, really astounding how human brains can do this. And this is why Doug Hofstadter, who's a famous philosopher, mentioned that the central problem in AI is modeling the letter A. Nothing more than that. If you can understand the letter A using AI, you can get general intelligence. So we solved CAPTCHAs, you can reCAPTCHAs and many other CAPTCHAs. They are all obsolete now. People don't use it anymore because they are cracked. And more importantly, it is how we broke the CAPTCHA that is important. And we stuck to these new brain principles of very little training data and being able to solve a wide variety of CAPTCHAs using extremely little training data. And let me show you another aspect. Another aspect is robustness. If you train a deep neural network to solve CAPTCHAs, it can do it well. But if you change the spacing of the letters in the CAPTCHA, the deep neural network will break. And so deep neural network accuracy will go down, whereas our system remains robust even if you change the spacing of the letters in the CAPTCHA. And this is the same system that we can use to parse scene letters. And also the same thing is currently being used in our lab and soon in production for parsing scenes in a cluttered bin and picking up objects, et cetera. It's the same algorithm that is being used in these settings. And the third one I want to focus today is build systems that can understand concepts. So if you want to tell a robot to do something new, how do you do that? If it is a child, you can tell the child, oh, pick up that red cup and put it in the green dish. How do you tell that to a robot? For that, robots need to understand red cup, pick up, inside, on top of, all these things. These are concepts. Currently, robots do not understand these concepts. We as humans build a rich set of concepts, starting from left, right, up, down, all the way to complicated concepts like democracy. How do you teach a robot these concepts? Without these concepts, robots will not get anywhere to the level of Rosie the robot. And this is something that we published recently in Science Robotics. This is about how do you teach concepts to robots. And the basic idea is this. So we got a bit of attention for this as well. So the basic idea, let me explain here. So let me show you a few pictures. So on the left-hand side is the input, and the right-hand side is the output. You can all see what is happening in those pictures from the input to the output. This is, you can see that we are taking the red objects and stacking them on the right, and the green objects and, arranging them on the bottom. So this is something a child would understand just from those pictures. Can a robot understand this? And if it can, then if you present a new scene, it will be able to perform the same task. So the task is conveyed purely through pictures. And you can think of this is what IKEA diagrams are. We get a bunch of pictures. We understand what is the concept going on in these pictures, and we then execute that concept in the real world. This is an element of understanding concepts. From pictures, you derive the concepts, and finally, you'll be able to connect it to language. And this is what we did. And the core insight here is that concepts are programs. These are little programs that we have in our head. It is like counting. When you teach a kid counting, you point to object 1, say 1, point to object 2, say 2, point to object 3, say 3. This is how you teach a kid counting. And this is learning a program. And the difference is that the program is not learned on a standard von Neumann computer. It is learned on a very different kind of computer that is in our brain. And so you have to learn that program, and transferring an input to the output, understanding what is happening is a set of instructions that you take from input to the output. And we did that. So we have this new architecture. We call it the visual cognitive computer. I didn't put it there, it's too complicated. But it has all the different pieces that go into our brain. There is a vision hierarchy, there is working memory, there is imagination, and all those things. And we have a primitive instruction set. And then, if you take an input to the output, you learn a program to do that. And now, what you can do with this is, suppose I give a robot these pictures. So you know what is happening in these pictures. So here, we are just stacking objects on the left. So you can just give that input and output picture to a robot. The robot will look at it. And then if you present it with a scene, it will actually stack the objects in the scene. You don't have to program the robot to do that. You just give the picture of, OK, this is what needs to be done. And there are many examples like that. In this case, the green object to the top left and yellow object to the bottom. And the robot will do that. And it can do this even though the scene changes. It is not the same objects. The background changes, et cetera. And arranging objects in a circle. Again, the idea is conveyed just through pictures. The robot needs to understand the concept to be able to execute that in the real world in many different settings. So that's the two things. So those are the three things that we needed to do to get to Rosie the robot. And I think we have figured out some of the very basic principles for building this new architecture, which is based on insights from the brain, and based on data efficiency, and based on teaching concepts to robots. So where are we going with this? If you look at a factory in the 1900s, this is what it looks like. It's a series of desks, people standing on both sides, maybe one side, and picking up objects and putting them together, maybe putting one on top of each other, maybe putting some glue on them, putting screws on them, and then finally putting in boxes. So this is what a factory in the 1900s looked like. And this is a picture of the factory in the 2000s. The only thing that changed is that we have now color. But otherwise, everything is still the same. It's still people standing and assembling these things. Why is that? The reason is that when the tasks change in the factory, it is very difficult to reprogram these robots to do things. That's because the robots do not have concepts. And so you cannot easily tell them, oh, instead of doing that, do this. You have to laboriously reprogram them. And with the advances that we have made, I think it should be possible to make the future factories much more autonomous, even when the situations change, even when it is a high-mix, low-volume environment like most of the manufacturing is. So that's our goal. That's where we are going. And so we hope that with our efforts, it will be mostly robots in future factories. In fact, we are sending our robots to factories, our first deployments, within a month. So wish us good luck on that. You can learn more about this by visiting our website, vicarious.com. And also, you can also follow us on Twitter. And you should definitely follow me on Twitter, because I have the coolest Twitter handle. It's called Dilip Learning. Thank you.
All right, thank you, Dilip. Oh, come on down here with me. We're going to do some questions from the audience.
OK.
So, come on down.
OK.
Don't be shy. That was very interesting. We're going to take a few questions from the audience. The first one up is from Anne, who asks, how would you explain social robots to a child?
OK, this must, I don't know whether this was a question for me or for the previous speaker.
Oh, you know what? You're probably right. OK,
Okay.
let's flip through that.
OK.
And we will, the second one is much better. So how will humans earn money when all work will be done from robots? And how will people from the third world developing countries benefit and win?
Yeah. So this is a very, very, very good question. And of course, this is on top of our minds as well. The history of automation is that when jobs are done by machines, yeah, it will displace people who have been working on that. But at the same time, it creates much more opportunities. There are several examples of this one. One is ATMs, the teller machines. When ATMs came out, people were worried that now the tellers will lose the jobs. But what happened is completely the opposite. What happened is that because counting the notes, that part is automated, now banks could open much more branches and let the counting be done by the machines, and tellers could do more, interact with the people and understand their financial needs, etc. So actually, the number of tellers increased in the United States, even though ATMs became more prevalent. So it is very counterintuitive what can happen with jobs. What will happen is that new kinds of jobs will be invented. I can show you, tell you a profession that did not exist 10 years ago, YouTuber. In fact, if you ask kids today, they all, many of them want to be YouTubers. This is not a profession that existed 10 years ago. And what will be the professions 10 years from now or 20 years from now when more of the mundane work is automated? We don't know, but there will be more work. And and things that we used to call work earlier will not be called work anymore.
So, yeah, so we can't really predict what the jobs are going to be.
Yes.
But if history is any indication, there will be other jobs.
Correct.
Yeah.
Yeah.
And then do you see this happening mainly in terms of robots taking over jobs for humans? Is that going to happen mainly in the developed countries, or will it take place simultaneously in third world countries? The infrastructure investment is so much higher than for humans. How do you think that's going to work out?
Correct. So it is. I think it's first going to happen in the developed countries more. The reason being, it's the economics that drives this. What makes, when robots are more economical than people, that's when adoption is wider. And we are definitely crossing that in the developed countries, but might not be true in the developing countries.
And at the end of your speech, you were talking about this sort of understanding concepts, the conceptual idea of moving everything to the left.
Yep.
What about moving on? Anonymous is asking about emotions and feelings in robots. What is the outlook for that? I think it drills down to common sense or being spatially aware of other people and how they're feeling.
Yeah.
Is that part of your work?
Right. So, so we do have to put in some drives in the robot, so that they will learn about the world. Things like curiosity, and also when it does something wrong, it needs to know that that is wrong. That is not the expected thing for it to do. This is what we call emotions and feelings, but it need not look like emotions and feelings to a robot. So unless we want to, play with robots and, fake human things in robots, there is no particular need for putting emotions into robots other than, so you can make robots do all the work that we want them to do without actually putting emotions in them. But it's only if you want that social component to it, then you can program in that emotion part.
All right. Okay, fascinating stuff. Thank you very much. A big round of applause for Dilip.
Thank you.
Thank you.